Okay, he can hear, but we cannot hear him.
রঞ্জন, তোমার সাথে উনি কাকে ফোন করছেন? আমাদের কাউকে?
জানি না, না আমার
কথা বলে না।
হ্যাঁ, কিন্তু আপনাকে আমরা শুনতে পাচ্ছি না। হ্যাঁ, সব দেখতে পাচ্ছি, কিন্তু আপনার কথা শুনতে পাচ্ছি না। মানে কোনো কারণে কোনো অডিও প্রবলেম হচ্ছে। হ্যাঁ, ঠিক আছে। না, উনি আমাদের দেখতে পাচ্ছেন।
ওকে।
হ্যাঁ, এবং উনি আমাদের কথাও শুনতে পাচ্ছেন, কিন্তু ওনার কথাটা আমরা শুনতে পাচ্ছি না। হ্যাঁ, গুড ইভিনিং প্রফেসর সেনগুপ্ত, এই দাশগুপ্ত, সরি।
আমি প্রফেসর সেনগুপ্ত আর মৈত্রী দাশগুপ্ত।
না, আমি মানে পাশাপাশি তো দুজনে এসে মানে একটু আমার গুলিয়ে গেছে। দুজনকেই অ্যাড্রেস করতে গেছি।
আচ্ছা আচ্ছা, নমস্কার।
নমস্কার, নমস্কার। হ্যাঁ, আপনার ইয়েটা দেখতে পাচ্ছি ডক্টর মাইতিস, আসছে, স্লাইড আসছে, কিন্তু আপনার অডিও আসছে না।
অরিজিৎ কি স্পিকারকে বলছো? আচ্ছা, ডক্টর মাইতি,
মৈত্রী কেমন আছো? তোমারটা বন্ধ করা আছে।
ভালো, তুমি কেমন আছো?
এই তো আজকে আমরা ওই ন্যাশনাল সায়েন্স ডে উপলক্ষে কলেজে গিয়েছিলাম।
কোথায় গেছিলে?
Can you listen me now?
I think we can hear you now.
Yes, yes. Now
Okay,
it is clear.
so I came to laptop mode. So okay,
Okay.
I think I can.
Can you just put your screen a little upright so that we can see your face?
Yeah.
That's better.
Oh,
now.
yeah, right. That's now much better.
And can you try sharing your screen?
Yeah. Now I'm opening it again.
Yeah.
অনুপম পাওয়ার সাপ্লাইটা নিয়ে আসবে। পাওয়ার সাপ্লাইটা নিয়ে আসবে। পাওয়ার সাপ্লাইটা নিয়ে আসবে ওখানে।
So just for everybody's information, the streaming is already on. So if someone
Okay,
wants
good.
to share it with their students, please feel free to share. And can you also click the hide button? Yes.
Yeah, now it is all set.
Yeah.
Good.
Yes, sorry for this disturbance.
Okay, let us start then.
Yeah.
Okay, so on behalf of West Bengal Academy of Science and Technology, I welcome all who are present in the Google Meet as well as in the YouTube live streaming in this today's program on National Science Day, which we all know is celebrated on the occasion of the discovery of Raman effect by Professor C.V. Raman. And on this day, most of the scientific bodies, professional bodies, they organize some programs. Now, so far, WAST has not organized, into the best of my knowledge, anything on this day. So this year we thought that we'll organize, but we were late in planning that. But thanks to Dr. Maiti for agreeing to deliver this talk. So we are holding this talk today. So without wasting much time, I would request Professor Ranjan Ganguly, our own fellow and professor of Jadavpur University, to give a brief introduction of Dr. Maiti.
Thank you, Professor Chakraborty. So we are lucky to have here Dr. Nakul C. Maiti for our guest lecture on Science Day. Dr. Maiti is an outstanding and renowned scientist in the field of biophysics and structural biochemistry. Dr. Maiti currently is a senior principal scientist at CSIR, Indian Institute of Chemical Biology, and also a professor, Academy of Scientific and Innovation Research, ACSIR. Dr. Maiti also has an impressive educational background. He did his BSc with chemistry honors from the then Presidency College. He obtained his master's in chemistry in 91. Dr. Maiti thereafter pursued his doctoral research at the Tata Institute of Fundamental Research, Mumbai, and obtained his PhD in 97. Soon after he joined his PhD in biophysical chemistry in January 1998, Dr. Maiti joined the renowned Institute for Molecular Science, Japan, as a visiting scientist under JSPS fellowship. There, Dr. Maiti's research using Raman spectroscopy discovered that the functional oxygen at the active site of xanthanite oxide remains unchanged during enzyme action. He continued his Raman investigation on biological samples and viral proteins at UMKC, Kansas City, USA. His expertise and experience added extra momentum on his research career and enabled him to undertake an NSF-funded project granted to Dr. Carey in 2001 at the Department of Biochemistry, School of Medicine at Case Western Reserve University, Cleveland, Ohio, USA. At CSIR ISCB Kolkata, he also developed a novel technique to quantitatively characterize unstructured protein states by Raman spectroscopy. Dr. Maiti is as such an international expert in biological Raman spectroscopy, and he was able to bring the unique use of own Raman discovery in biological research in India. However, Dr. Maiti is also an expert in FTIR, NMR, fluorescence spectroscopy, and molecular dynamic simulations. Dr. Maiti's research contribution enabled him to be a full member of the American Chemical Society and the Sigma Psi, the Scientific Research Society in the USA, and several other scientific societies in India. He is honored with the Springer PSI Proteomics Society India Award in 2019, ACRB International Travel Grant Award 2015, and the JSPS Fellowship Award at 1998, Japan. Raman Fellowship Award by CSIR 2012, New Delhi. Dr. Maiti has authored more than 100 research papers in international journals of repute and 4 book chapters on amyloids research by Raman spectroscopy. Several students received their PhDs from Calcutta University, Jadavpur University under his able and unique guidance. This year, Dr. Maiti is selected as the Fellow of the WAST. So let's welcome all Dr. Maiti, and we are sure that he will enlighten us with some unknown facts about Raman spectroscopy. Over to you, Dr. Maiti.
Okay, thank you very much for, first of all, good evening to everyone. And thanks particularly Dr. Professor Chakraborty and Dr. Ghosh, and you just introduced me. And yes, okay, actually just after my PhD, I was thinking, because at TIFR, there's a note is that if you do PhD in some field, we have to think a little bit different. Then, as you know, that TIFR located at that sea, and that actually Raman discovered whatever Raman spectroscopy seeing the sea. So we thought that, okay, I can move a little bit from fluorescence to Raman. So that's my journey started in Raman spectroscopy. So immediately after my PhD, rather before PhD, I got JSPS. So I started my work in Japan. an IMS. That is, during that time, resonance Raman spectroscopy was the height. So I started, and that is the journey. Still, I'm continuing. So today's day is special day. All you know, this is the National Science Day of India. That is the reason I'm making this presentation. I may not speak totally whatever I'm doing in this laboratory. I may get a chance in future so that I can talk about much more detail about my scientific, but I'll touch, of course, as I mentioned it here. So today's talk will be journey towards modern biology about Raman spectroscopy and its discovery. So I quote this here, as I mentioned, this is the special day, and also special for me because I am sitting next to the building where Raman get a chance, or that institute, IACS, Indian Association for the Cultivation of Science. And so I'm lucky enough today that about 100 years back, a little bit less, but our Sir Chandrasekhar Venkata Raman could get and do wonderful job that time, and got a Nobel Prize, and that is the celebration we are doing. And so I'll start that way. So it will be a little bit about, I'll talk about the discovery and how Raman get this Nobel Prize, and then simply I will touch that how it is progressed and how this Raman spectroscopy is today in almost every field of biology and medicine it is coming. And so I'll touch that one. And so let me start that what Raman effect is, that simply to say that, so what he said, that when a beam of colored light, so basically to see the Raman effect, if a particular color light pass or enter to the liquid, a fraction of the light scattered by that liquid was a different color. That was the observation, and that was the discovery, of course. And Raman himself claimed that this is a phenomenon whose universal nature has to be recognized. Okay, and that is called the Raman effect, that if you simply pass any light, and what is I said, and I could detect that things. Imagine that, and that he can detect it and he can prove that. So if a simple light pass through, not only that light, all lights can be coming out, and that is the Raman phenomenon or Raman effect. But this is every day, everywhere it is happening. On the screen, whatever light you are seeing, there is also Raman scattering, but we cannot detect it. Okay, we cannot separate them, what the color we are seeing on the screen. So that is the only thing that, but as a scientist, we are from the natural research, we can identify that. And so in 1920, okay, so this is not the year or not his birthday that we are getting this Science Day, National Science Day. And this prize was given him to 1930. All we know that that's how the 28 as National Science Day and in India. And actually this is proposed in 1986 by National Council for Science and Technology Communication, that is Indian governing body that suggested these things, but it is slowly getting to picture, and nowadays in everywhere, in every research institute or education institute, or even in a school level, this program is running. And this year, of course, this is a special again, because this is the indigenous technology for Viksit Bharat. That is the motto of this year National Science Day. And that way also it is important that we could have, I'll talk about that, last year, that is the first indigenous Raman spectrometer we can build after 100 years. So there is a joke that it took almost 100 years to come from one building to next building, means from ICS to IICB, CSR, IICB. And so that way it is also matching to the this year's National Science Day initiative, that indigenous technology for Viksit Bharat. And also I want to mention it here that this discovery, of course, Raman made it by working in Indian Association of Cultivation of Science, that what Mahendralal Sarkar, he was initiated around 1817, if yeah, 87 mostly, yeah, if I'm not wrong. So that institution was also made for the purpose that so that indigenous people, mean people who are really can contribute without the much more effort from the much more contribution from the government of British government in India. So that is also indigenous. Dr. Konkon, our late Professor Konkon Bhattacharya, he has mentioned in the memory that So that was the contribution of Mahendralal Sarkar. He was trying to get indigenous people to do science without help from the British government. Exactly now we are trying without boarding or without getting the Raman machine from abroad. We are doing these things indigenously, the help of our CSR Bhopal and also Techno's instrument, Gujarat will we can get the very good Raman spectrophotometers. So it is matching with those things. So as we are talking about the Science Day and Raman discovery, we have to mention about, although most of us, we know all these learned people, we know that how this discovery was made, but as this day is special occasion, I just briefly mention that this ambience, particularly the sea, how it affects that. Sir Chandrasekhar Raman actually born at Tiruchirappalli, and then but his most education was near Presidency College, and he was living in the within the sea was always with him. Maybe from the very beginning, he started to think about the looking at the sea and how that color is happening. Anyhow, he earned his MA degree at a very young age from Presidency College, and before he got his MA degree at the age of 19 years, he published 3 unique papers in Philosophical Magazine and also Nature. So that was the things that by the age of 19, he could publish 3 papers, unique paper. Of course, he was working on basically vibrations of the string or musical system. Also, he was practicing or basically doing experiment with a diffraction diffractometer, how those things can be done. And of course, as all you know that around 1907, the year he passed the MSc degree, exactly that time he also got the basically finance department government job called assistant accountant general. That was a competitive exam. He stood first. He took that job because that time he felt that money may be required, and he took that job because that is the best job where you cannot have any foreign degree, but that was a decent job. So he took it, and he was posted in 1907. So in his previous, I mentioned it here that plentiful sunlight in Calcutta. So this has 2 meanings. He mostly this is his word. He maybe wanted to mention that plentiful sunlight here, not only the light source of sun, because but also the intellectual environment of Calcutta. So that is his intention to mention. And so in 1907, he landed in here with a government job, and with the part-time means after his office time, he could do some work, and he could publish many papers. And so, he left the government service, joined the University of Calcutta with the Pali professorship and Shama Prasad Mukherjee. And so he's a wonderful man. He could imagine, and he was awarded the Pali professorship, and he took it even he didn't have that time any doctorate degree. But he said he he could manage with his because by that time he has published so many good articles, 20 or more, and he was given that things, and he then successfully continued for 10 years, and he could discover this Raman in 1928, February 28 basically, and then this paper was published in Nature, and he got Nobel Prize in Physics, particularly in this is the pictures at 1930. So as I mentioned, so we have to think about it, how this discovery was made, because as I mentioned that light can pass through, it can a Tyndall effect. We have seen that it can give slightly different color when light is passing through, but that is the eye we'd have. So after getting Nobel Prize, of course, he wrote this about a couple of years after when he is in Bangalore. So for nearly, he has the debt to the Calcutta, and he mentioned it that for nearly quarter of a century he stayed here, and he has great things to say that Dr. Mahendralal Sarkar and Sir Ashutosh Mukherjee, actually he is indebted to me, and also thanked Calcutta people because of this, and in expression of gratitude after getting Nobel Prize, where people honored him. And so he still liked this Calcutta and particularly their environment, but there are some controversy, but that is the intellectual interactions, but he could overcome that things, and he is indebted to these things. But how he got this Nobel Prize and what were the thinking? So little bit I'll mention it because today is the discovery date. So by the time all we know that quantum theory and quantified nature of the energy, that was the beginning of that century, or the 20th century beginning. That time it was people are thinking that Einstein theory, that quantified nature of the light, and also that time what we know that rainbow color can diffract and scattering, those things were known. So very much, but as you know that around that time we discovered that light and all those things, that quantum, so that was actually they are studying, and also the diffraction, so he has studied. So that time everybody know that light falls on anything that could scatter, and that is the common thing, Rayleigh scattering. That theory was there 1910. So it was well established theory, and he also explained. But when he was coming from the England, so he was not ready to accept the concept, because from the very beginning of his life he was thinking, see, it looks blue, maybe different reason. Okay, so he immediately after coming from London, he landed in Bombay Harbour, and he sent back this letter to the natures that whatever Rayleigh claimed, and that is, he also got this idea that whatever the blue color of the sea, the deep blue color is due to the reflection of light by the air molecules, and that is reflected back to our eyes. So that is the cause of the, and that discovery by Rayleigh was also made by a voyage for a couple of years, 1910. But about 1921, about 10 years after, when Sir Raman was traveling back from the London, and he realized that it is not the color due to the reflection from the air particle in the sky, but it must be due to the water molecules in the sea. So what it helps, because he has one very crude spectrophotometer what he made simply by nickel prism. We all have like little bit physics background. The nickel prism, you can rotate it in different angle, then you can reduce the reflection or light which is falling on the sea. And if you can look in other direction, then what he noticed that there is a deep color, different color without any reflection. So that is simple nickel prism. He made the spectrograph oriented different direction throughout 15 days or 20 days of his journey in the sea. So he was confirmed that it must be water molecules. So he could not stop his mind. He wrote the letter, sent it to natures. So such a wonderful thinking, and he was waiting to prove it. So that proof has come in the laboratory. So what he did, so he imagined it is correctly that light, whatever it falls, that is going back, that is scattered, Rayleigh scatter, it is fine. But there is small amount of light that is called inelastic scattering. So that could be the region that is associated with the molecules, and that is his credential was that he could identify, he imagined that it must be different color of light that is coming, and that is called inelastic scattering. And his credit was that you imagine 1 in 10 to the power 7 photons generally you can see as a different color. Okay, so that is a very weak. So you cannot see, it will be hide in the sea, but that's how his credit starts. So he could measure that. He could not, he sent the letter, he could not wait for that. He came to the lab and he started the experiment with simple instrument, whatever it could measure. Okay, so what he did, simply he used simple liquid like benzene, toluene, several organic liquids he took and passed the light, sunlight through some filter paper. What is a simple filter which can you give the green light or something, and that is when it passed through this, what you see that apart from this bright light which is due to the and he also was clever to use mercury lamp, where lines mercury from the mercury lamp, the light waves, they are coming quite a different wavelength, there is a gap. So he used that light intentionally and using and also sunlight sometimes. So what he said that whatever the line is coming, apart from that, there is just some other lines which is little low in energy or longer in wavelength. So that time unit was not centimeter inverse, still wavelength. So these lines, so he could detect it, he used around 60 solvents. So he could publish that, and that was his proof, whatever he observed in sea and what he wrote in Nature. Then now he has the experimental proof, and then of course Nobel Prize. So two things. There is K.S. Krishnan, he helped also, he was working also with him. So he also helped him to see that not only low frequency or lower, higher wavelength peaks, but high energy line also could be seen. And also another discovery was that all the lines or light coming out, they are polarized. Okay, their particular polarization is there. So these are the two important observations they experimentally proved with very simple, either sunlight, using sunlight and very simple sum of the mirror and spectrometer, he could detect it. So he could publish it, and that's how he got the Nobel Prize. So it is, the idea is that not only that this light it could be done, but as I mentioned that so there is infrared, all you know, by that time infrared is coming, but Raman spectrum is like that. So you have to excite the molecules that will be scattered back, so we can detect it. So it could be Stokes line or anti-Stokes line. Again, the beauty of these things that it depends on the molecule, and we could have 3n minus 5 or 6 number of fundamental vibrations that cause the, and so many Raman bands we supposed to get it, but not, of course, not all will give. So there are many things there. So, but we need a intense light source and also unique wavelength, so that from the molecule, as it is the change in the frequency, so it should be pure particular energy, and also intense radar source we need, because it is a very insensitive technique. And again, if we go back to, instead of vibrational, also we can have rotational Raman. So we forget the rotational Raman, even this vibrational, which is linked to each and every bonding of a molecule. So that's how this, whatever he imagined that it could give the molecular signature, that is now coming true, and that's how the discovery got Nobel Prize. Okay, so it simply we need a laser source, because as I mentioned, 1 in a million photon only will be Raman active or Raman sensitive. So for that we need an intense laser source. Then of course all we know that filter that gratings, and this is the simple detector. But nowadays with that lasers and optics and everything, this is the example of even protein spectrum. So Raman could be highly excited if they see that we could have a protein spectrum is that extended quality, and each peak of these regions, okay, that carry information. So that how this is my own spectrum recording. So we could see you each peak, what you call, or sometimes we call peak, sometimes band, that doesn't matter. So each are related to some kind of vibration or of the molecule or the band. So we can identify these things. And one beauty thing is that even 0.001 Armstrong, which is much better resolution than your crystallographic, if that much change is there, this band will be changed. So we can identify what kind of interaction is happening and all those things. So each band carrying many information, particularly I'm telling for protein molecule itself. So all small molecules, of course, we know that could be identified by IR and all those things, but I'll mention what are the advantages are there, but we can get unprecedented, very impressive spectrum of protein sample or even biological sample by Raman spectroscopy nowadays. Okay, so what happened after, as I mentioned that, I will briefly mention that how Raman spectroscopy, after discovery, what happens. So as I mentioned, 1930, there was no laser, no intense light source, of course. So after the discovery, around 10 years, only 700 papers came. They are all, basically, they are proving this concept, how the molecular vibration can be judged, whether it is following that quantum chemistry or quantum physics, quantum dynamics, whether it is valid or all those things, basically physics-oriented works. So it was proved everything is perfect and working fine, but there is no others like source. As I mentioned, you needed very intense laser source and optics. So it was just like that. And then, of course, it slowly started to come to chemistry, because it is all molecular vibration can be detected. So as Hivans mentioned, that Raman effect became the adopted child of chemistry. But still, it was not very much used as an analytical technique, but it was started as an analytical tool, but not very much used. But laser was discovered, that Mindman discovered the laser in 1960, got Nobel Prize 1964. So that is the start again or revival of Raman spectroscopy, because now we have the lasers and now we have the intense band and proper energy. So now, around 1917 to around 1985, like that things. So Fourier transfer technique also developed, and also some optical advancement. So some of the experiment was done, and so lot of what we call resonance Raman, where the molecules separate absorbed there, we can get the Raman spectrum that was started. So that means there also we can get very enhanced number of peaks. So around that time, using a Fourier transform Raman, just like FTR, we can get, that is during that time many people started working on metalloproteins like hemoglobin, myoglobin, and cytochrome C, like that. So during that period, that started up to 89, like that it was started, and 1990 to 2004, 24 now. Several, because of the different type of Raman techniques that techniques has been developed in every aspects of biology, it is coming, and so it is like huge burst because of the computer and also software and many other things. So nowadays Raman spectroscopy is all aspects in biology, it is entering. So it has several advantage. It is a non-destructive measurement technique and label free. In fluorescence, if you want to label any biological sample, we generally label with a fluorescence, but Raman we don't need it. And also is non-destructive, means even if you take in a skin or in a cell, it will not die, it will not give so much energy, because 1 milliwatt or less than that energy, you can detect very good quality of Raman spectrum. Another beauty is that you can use in any solid, liquid, gas, everywhere. So it has universal application nowadays, and it is a femtosecond phenomenon, easy to do kinetics. Like our cellular experiments, many things are in micro scale events. So Raman techniques or kinetic Raman spectroscopy is another technique is coming very much, and also femtosecond excited state Raman phenomenon. Those are the physics that is also going on. And also another beautiful thing for biology is that Raman can be easily applied for aqueous substance. IR, it is very difficult in aqueous solvent. Okay, so IR spectroscopy is not that very useful for our biological sample, but as water is not that effective, so Raman can be easily used for aqueous substances. So it can detect and quantify biomolecules with high precision, sensitivity, and specificity, and also it can diagnose tissue in situ information faster than traditional lab methods. If you can have it nowadays, handhold probe is there, you can take it and can so multiple measurement configuration like microscopy and endoscopy, everywhere is now laser. Today morning from German consulate, people came and they were giving a talk about funding and other situation. They mentioned that some experiment where high pressure is required, like that they are fusing the diamonds, and so basically phase transition and all those things at high pressure, like 3000 and more than kilopascal. So what probe can be used that there is a phase transition, how the fusion is occurring? So there is a probe is the Raman. So Raman is such a unique technique because it can be useful for many purposes. So as we mentioned, so still earlier up to 2000, it was manufacturing process, petrochemical analysis, how much petrol is there, how much different component. Of course, pharmaceutical industries, forensic science like illegal drug analysis at spot, paint industry, whatever the material they are putting for many purposes, almost everywhere this technical instrument is there nowadays. Analysis of nuclear waste, it can be probe, you can enter, and safe distance you can measure. Almost each Gujarat, if you go any stone factory or everywhere, there is a small Raman spectrometer. It can easily detect which is diamond, which is not actual diamond, or everything you can detect. And photochemist, of course, photobiologists, they are doing transient measurement, whichever even 10 to the minus 11 second. We can do nowadays another called surface enhanced Raman spectroscopy. As I mentioned, the technique is weak, but if you put it at some nano surface or something, so that 10 to the power 4 or 10 to the power 5, that scale, that peak intensity could be enhanced. So that is helping now doing many in vivo experiments, cellular experiment. As I mentioned, that condensed matter physics also we can did it. So it has a huge use. So I'll cite only 2 experiments where I did it earlier as introduced by so that I did some Raman experiment in Japan. So during that time, as I mentioned, that lab was not of resonance. We are putting the only the resonance Raman. What is resonance Raman? Now where the molecule absorbed light or there is absorption band like your porphyrin or other molecule or blood sample, they have a heme group. So they absorb light around 400 or like that regions. So if we excite that light with a laser which has the absorption near the absorption band of the molecule, you will get a night spectrum of that molecules. Okay, it is the prosthetic group of like this is the xanthine oxidase uric acid form. You know, many people are suffering from uric acid problem. Okay, that is the there is a molybdenum cofactor of xanthine oxidase. That xanthine oxide what it does in our body, it produced uric acid. Okay, so it is also known an enzyme, but long people are not knowing that where from oxygen is coming when this is reduced form. So there is a turnover that it will be active form, it is reduced form, and in the transformations, so they basically oxygen, which oxygen is involved, whether the oxygen is directly transforming this oxygen or from solvent H2 molecules. So I did that experiment, Raman experiment, and so what we proved that you see the different spectroscopy. So you have to be very careful with Raman analysis. So you have to have precise measurement. So when we substitute with sulfur chemically, and then we get a nice peak, and doing many other experiments, we proved that for the first time that this oxygen which is transferred from xanthine to xanthine oxidase, that molecule I have not given. That is basically coming from the water. So that was wonderful. After 100 years of speculation, we could show that oxygen is not coming from directly from the molybdenum center of the enzyme, but it is coming from the water molecules. So I am not elaborating that things. I'm touching one other point which I'm currently doing at CSR IICB. That is, we are trying to establish some kind of, Parkinson and Alzheimer disease. That is, though it is old age disease, now as the aged population is growing, so there is no cure, or we need some kind of solution. Okay, detection also. We cannot basically, when people we are suffering from Parkinson and Alzheimer, it becomes basically, it may have started quite long before, but there is no solution. What in this disease characteristics from the scan of the disease head, that if you scan actually this is the kind of inclusion bodies which we have here. So this can be found, it is actually from the sample, brain tissue sample. And then if you go a little bit microscopically, you can see that by staining that this kind of fiber kind of things are there. Okay, so this is from the postmortem brain. But there is no way to do structure, NMRs, X-ray, nothing will help in this regard, as I mentioned. But that's how we started in the Cleveland Case Western with the Paul Carey, that whether we can do something amyloid research with the proteins linked to, this is called the alpha-synuclein protein and A-beta for Alzheimer. And so these proteins, they form this kind of structure. So our idea was that whether we can detect it in some, and what are the structure of this protein when they are in disease formations, and whether we can detect them a little bit early. That was the idea, and we started that, and I'm continuing that. So what we observed that this is all our in situ experiment. You can see that protein which we see in the brain of a Parkinson disease patients. So we can make it similarly in the laboratory. Then we started getting the structure of these things. No other technique could give any informations, but this is the FM picture of those species. And then if we do the Raman spectroscopy, you can get this kind of Raman spectrum of this called the alpha-synuclein protein. So we reported this alpha-synuclein protein, and then that is called amide bond, that is characteristic. So this region, particularly that 1674 regions that give unique information of this protein by Raman spectroscopy. So we get this information from here, And we analyze this, and we do a lot of experiment. And so I'm not going into the details. The what is take home message is that using Raman spectroscopy, this is of resonance Raman, just we took the sample, put it under microscope, Raman microscope, and we can get beautiful spectra. Then we analyze them, what is those peak position or vibration mode of the amide bond, how they can give different information, and this different number in terms of frequency or energy, they are carrying the information, what is the state of this protein secondary structure, which is alpha-synuclein for Parkinson disease. They are in different state when they are forming oligomer, like a globular species which can pass through the cell membrane, when they are forming fibril kind of things, which is the end product or end things which we see in the patient head. So all the structural information we can get it by Raman spectroscopy. See, here is the spectrum. It is called oligomer from the same species. So they are not transforming into fiber, but these kind of globular species could be the reason for Parkinson disease. And so that we can get and we can establish their structures. And we found that there is a alpha helical nature of this protein even in these conditions. So now also we are doing insulin. You know, insulin is a very stable protein, and but it is, you have to put it in a cold, refrigerator or somewhere for its specificity. Sometimes it get denatured, and also if you take insulin injection, there will be some aggregation, protein can fiber, and all those things. So we have used data with collaboration with Anirban Bhuya at the Bose Institute, and we have showed by NMR and Raman spectroscopy how we can overcome these things and what are the cause the protein aggregation, what are the necessary things, whether we can manage some molecules which could stabilize. We have done a lot of things and a lot of results we have published recently. And for this, very recently, actually this is the published January end, and it has not even number is there, but we have the DOI number. So I consider this a tribute for my National Science Day. So we have shown that insulin, how in water can be phase separated, even in the soluble form. So this is the physical Journal of Physical Chemistry paper, SCS, but still it is a very unique information. We showed that insulin, where there is a disulfide linkage, like there is a 3 disulfide linkage, they are in different conformations, but when they form the fibril, they get a unique conformation like this. So this is that disulfide linkage information, this region, and this is the protein secondary structure information. This yellow line, that is actually when it's a monomer, pure monomer, but this is the cyan color, that is the where it from the fiber. So a lot of information we can gain these things. So as I mentioned, that Raman spectroscopy now entered in all fields of biology and medicine. It is for blood sample, we can do it, and we can do label-free living single cell analysis, immunoassay for tuberculosis, medical diagnostic assay to in vivo cancer detection, biomolecular snapshots of mitosis, healthy and cancer cell using plasmonically enhanced Raman spectroscopy, what we call surface area Raman spectroscopy, identification and classification of cells, monitoring the content of proteins, lipids in a cell, differentiation of stem cells and other cells, observing effects and change in inductor, many other things we can do, like stem cell research. Many people know. So we have a Raman probe, means we can do it. We can identify it, whether it is the stem cell or it is the natural cell. So many things, all everywhere it is there. I am not discussing that things. So as I mentioned, last year you could house this in Raman spectroscopy. This is the India-made Raman spectroscopy. Software is completely from India. Only that some of the optics is basically we borrowed, but most of the things is made in India. It is made by the help of Technos and CSR Bhopal also help it. So this is the first indigenous Raman spectroscopy we could house in our next to cultivation in IICB last year. And this company, they have get ordered for 7 such machine making in India. So it will help the what is called Viksit Bharat program. So it really a good contribution for this National Science Day. Okay. So what I am doing in trying to do, and we are trying now using this Raman biomarker for AD, Alzheimer disease and Parkinson from blood serum sample. It is not that easy, but we are trying to develop, if we can successful, in situ and in vivo study of phase separation. As I mentioned, I have shown initially, and phase separation is also nowadays and biological in like for COVID and many other things, that for protein storage and many other purpose, phase separation is now a hot topic. So we are trying to understand phase separation inside the cell using this Raman probe. And as I mentioned, we are also developing nano dots or quantum dots and nanoparticles for cell imaging and spectral enhancement. So we have submitted some patent, and also it will be, I think we can come across with more in next time. I may, if I get a chance, I could talk to you in a seminar that exact science, what I'm doing. And of course, for last, I am here, I joined CSR IICB in 2010. And so about 12 years I worked here. And so these are the students who have contributed a lot. And also I should, Raman Research Fellowship Award and Department of Biotechnology for my first Raman machine, which I bought around 10 years back. And also CSR, of course, their funding, also some grant. And I must thank you for listening in this evening. And my special thanks to Professor Chakraborty and Ghosh, who initiated and also give me opportunity to speak. And also I thank especially Mutridi, Chandrimadi and Shamalda Chitradi for their all encouragement, and all other WAST Council member also make me to be member of this in this year. And I thank you all. And I hope you have any things to ask me, you can ask me. I'll try to answer.
Thank you, Dr. Maiti. Thank you very much for giving an overall view what you are doing using Raman spectroscopy and similar things. So if any participant can, want to interact, they can raise a few questions. We have some 5 minutes time. So Dr. Mandal, Dr. Chitra Mandal has raised her hand.
Yeah.
Please go ahead.
Can you hear me?
Yes.
Please.
It's not a question actually. Already Nokul has shown in his future direction. We really would like to see your future direction, especially in Parkinson and dementia, diagnosis from the blood sample at the very young age, because usually they said it's an old age, but nowadays we find a lot of patients even at the young age. So that will be my suggestion to, for your future direction, as you have already mentioned from the blood sample. So that will be really helpful, really helpful.
Yes, Chitradi, yes, we actually submitted one project also, ICMR project, but that was not funded, but we are trying. And only thing is that if we could really from serum, it would be wonderful. Because many people are trying from some studies there from your CSF, spinal fluid, but that is very difficult and to get it, and also it is not easy job. So, but for blood sample is really some immunoassay method people tried from AIMS, but that is failed. So, because that protein get phosphorylated. So if you can detect that particularly, so what is my plan, or what I am trying rather? So we have two components. One is called principal component analysis of the Raman spectrum, and also to get this serum plenty of sample. That basically we are trying. Let us see if we can do it. Yes, I also believe if we can do that, that would be wonderful. And so
Thank
really
you. Thank you for your nice presentation. It was very lucid. I really enjoyed it. Thank you.
Thank you.
If there is any other participant want to raise any issue, any query, any clarification?
No, just a comment.
Okay.
Congratulations for the beautiful talk.
Okay, thank
you. Very beautiful talk.
No,
thank you,
I was thinking
Yeah,
that
please go ahead.
I was thinking this is a science day, so that's why I didn't make my scientific presentation that I didn't focus on my research itself, but I tried to make this occasion and also a little bit about my research I mentioned. Yeah.
Very interesting.
So now I request Secretary WAST, Professor Maitri Dasgupta, to present the vote of thanks.
It's my pleasure. Dr. Maiti, thank you for actually accepting our invitation in such a short notice. And I'm pleasantly surprised to see that you have been working on Raman spectroscopy for such a long time, which I was not aware of actually. Though I heard some of your 5,000 word seminar, but today I could relate what you was talking. And it's nice to hear actually. I didn't follow, and I won't say that I followed everything because I couldn't even follow if all your assays were being done in pure protein. When you do a diagnostic, there will be so many other spectra, overlapping spectra. Then what will happen? This is where I'm getting confused.
Yes,
So
ma'am. It is true that serum will have a lot of protein, other
lot of
proteins.
proteins, yeah.
Yes. So that is the things. But this it is known that when in Alzheimer's case, for example, that tau actually, even in Parkinson, tau protein get phosphorylated for Alzheimer's case, and also in Parkinson, some of the phosphorylation is occurs some tyrosine residue. It is known. So now what we are trying to do that. So if we take in Raman spectrum of on surface, like nano surface, it enhanced quite a lot. So that's fine. Still your point is valid that there will other protein also will enhance. So there it is coming the mathematical analysis, what is called principal component analysis. So if we can do that principal component analysis with patient sample and healthy sample, and then if we could have a plot, okay, or analysis like diagrams. So if we can fit that I hope that could be useful.
One way of doing it. Yeah, sure. That is your research all about to get to that point. Yeah. Congratulations on that. And finally, I also need to thank our president because it is his idea to actually celebrate National Science Day and for the academy, which was never done before, as he said. So even though that we have a small crowd, but I'm very happy that we have been able to keep up the spirit of science on this day. Thank you all very much for attending and being part of this lecture. Thank you, Dr. Maiti, once again.
Thank you. Thank you, Professor Dasgupta. But one thing, this will be archived in the YouTube channel of WAS, so it will be available that this was done. And Dr. Maiti, could you please stop sharing at your end? Then I want to share one thing. Thank you. I hope you will be able to see my screen.
Yes, it is coming.
Okay. Now, can you see this? The certificate of appreciation?
Yes.
So, Dr. Maiti, on behalf of West Bengal Academy, I present this certificate of appreciation to you. The hard copy after printing will reach your office. So please accept this as a token from West Bengal Academy. So finally, I would like to say that, as I said, this entire program will be archived in YouTube channel. But for that, I have to thank one particular person who has really worked with us. That is Mr. Arijit Saha, a PhD scholar of Jadavpur University, who is handling this matter single-handedly. So thank you, Arijit, for your efforts. So
you can stop sharing now.
Yeah, now I'm.
We'll all log out. Thank you.
Yeah,
everyone.
but before that, can everybody put on, just camera so that we can take at least one screenshot? Arijit, you can take. Arijit Boral, can you take the screenshot?
Yes, sir, I can.
Yeah, please, Dr. Mondal, and can you please put on the camera, please? And Dr. Helena.
I would request everybody to switch on their camera.
Although we are missing the speaker.
Yeah,
Unfortunately.
but speaker were suddenly missing, no?
Yes.
Oh, that was something not good.
I have taken screenshot during the
Yeah,
presentation.
okay. Oh, you have taken, no?
Yes,
You
sir.
have
that's
taken
all
only?
right.
Yes,
Yeah.
sir.
Okay,
We have
then it is
taken.
fine. Now you can
That's
take one more, huh?
Okay, sir.
Yeah.
It's done. Thank you.
Okay.
Okay, so
So,
thank you very
thank
much,
you, Varijit.
everybody.
You can stop sharing and screening.
So now
Okay,
we
then.
can log off. Bye-bye. Good night.
Bye.
Good night, sir.